Welcome to part two of rocks. In part one, our discussion focused on the three rock types with brief statements. We looked at the rock cycle and talked a little bit about what the rock cycle represents with regards to how rocks form and can transform from one rock type to the next. Then in part one, we looked at igneous rocks. And we looked at the processes, the common processes, if you will, that formed igneous rocks, where the magma either cools below the Earth's surface or becomes lava above the Earth's surface, extrusive and intrusive rocks. And then we specifically focused on the texture of the rock and composition of the rock, and then we set up a simple classification chart in which you will learn the 6 common rock types. And so we're going to move on now and talk about sedimentary rocks, and we're going to apply both texture and composition and discuss how sedimentary rocks are formed as well. So if you look at this first slide that you're seeing on your screen where it says sedimentary rocks, what do you find different in terms of the overlaying sedimentary rocks versus what you learned in the previous part one discussion of igneous rocks? And most students will look at the slide and say, wow, it looks like sedimentary rocks are layered. And in fact, that is a huge difference between the processes that produce sedimentary rocks and produce igneous rocks. If you look at the bottom part of your screen, you see a little truck, SUV, it looks like, that's down there, and that's life size. I mean, that's kind of gives you an idea that the amount of sedimentary rocks found on the Earth's surface is tremendous. And here you can see that the sedimentary rocks are typically layered. So how is a sedimentary rock formed? So what we're going to see in this next slide is basically a flow chart in which processes take place that will finally form a sedimentary rock. So for example, we'll start with a pre-existing rock. That pre-existing rock, again, can be any one of the 3 rock groups. Igneous, it could be another sedimentary rock. Metamorphic rock will allow that rock to exist on the surface of the Earth, where it's exposed to erosional processes, water, wind, ice. And the goal of weathering, in this case, or these erosional processes, is to break that pre-existing rock into smaller pieces. And as mentioned in part one, we're going to spend an entire discussion just talking about weathering. But for right now, we're going to take that pre-existing rock, we're going to break it down into smaller pieces, and we're going to break it into what we call sediment. And sediment represents loose, and I'm going to use this word unconsolidated. So I'm going to repeat this word again. Loose, unconsolidated, meaning that the pebbles and the smaller particles aren't glued together. A good example of something that's unconsolidated would be beach sand. So when you're walking along the beach and you grab a handful of sand and let it run through your fingers, this would represent something that is sediment and it's unconsolidated. And if you look at the pictures of the sediment that I have on the screen, you can see that sediment looks different than other sediment. For example, some sediment can be very rounded, elongated. Some sediment can be angular. Some sediment can be what we call poorly sorted, meaning that it ranges in all different sizes and so forth. And just that alone tells the sedimentologist or the geologist where that sediment came from and how that sediment moved and so forth. Some other sediment you may be interested would be this one. This is a little joke. Of course, this is pebbles from the Flintstone. And if you ever want to get any type of geologic knowledge in terms of vocabulary, just watch the Flintstones. And you see a lot of vocabulary. So there's pebbles. Okay, so we're going to take that sediment then, and that sediment then is going to be transported. So we have not made a sedimentary rock as of yet, because sediment is not a sedimentary rock. So we'll take this sediment, and there's various ways and processes that the Earth utilizes to transport different types of sediment. probably one of the main dominant ways is through rivers. And rivers can take sediment and transport it, certain amounts of distances and so forth. And depending on the energy of that particular river, sometimes you can transport very large type sediment with a lot of energy in a river, or sometimes if the river doesn't move very fast, then it's really confined to smaller types of sediment. And again, that's another way a geologist can tell an environment is just by the size of the sediment. So for example, look at Kern River in our own backyard. That river is considered a very young river, and certainly towards the headwaters of the Kern River, it moves pretty fast. So that would be considered a high energy type environment, which more than likely can carry some pretty big types of sediment. If you look at your screen, you see that another way to actually transport sediment is through lakes, for example. And lakes would be the opposite in terms of the energy from a river, and lakes are very quiet waters or very low energy. So if you were to throw sediment into a lake, more than likely that sediment would slowly sink down to the bottom of the lake, and it would arrange itself from very coarse type of material to very fine type of material. So lakes would be common to very fine material. There's other ways to transport sediment. There's wind. What would you expect wind to be? A high energy or low energy type transport? Well, in most cases, probably a lower energy. And thank you for that, because if it was high energy, we'd have a lot of problems during wind. Glaciers, for example, low energy or high energy. Well, glaciers represent a huge movement of ice bodies. And so it's actually low energy, but because of it's a huge body of ice, it can move big stuff, but very slow. So again, there's all sorts of different types of transportation mechanisms that can move sediment. So the question now is, what if the transportation mechanism for a river, for example, runs out of energy? So envision this river moving across the land, and it gets into a situation where the gradient becomes low and the river begins to run out of energy. What's going to happen to that sediment that's being suspended, for example, in that river? And typically what's going to happen is once the energy runs out, the river will what we call deposit the sediment, and the sediment becomes stopped, if you will, resting at some type of what we call depositional environment. So we could have a beach depositional environment, lake depositional environment, desert depositional environment, continental shelf depositional environment, a whole host of different types of depositional environments. But basically, it's where the energy subsides and runs out, and whatever sediment is being transported just kind of falls, and under the influence of gravity becomes deposited. So guess what? We're still not a sedimentary rock yet. So once it's deposited, we can envision that the sediment stays there for a long, long time. And as more sediment stacks on top of the older sediment, now that sediment becomes compacted and squeezed, and in some processes becomes cemented. So the sediment is actually glued together, and then once compacted and or cemented, we finally make a sedimentary rock. So in order to be a sedimentary rock, it has to go through a whole huge process. It's got to be eroded, turns into sediment, it's transported, it's deposited, and then it's lithified, which is a key word at the bottom of your screen. So lithification is a term that means basically the sediment has been glued or becomes a solid together. So basically it represents an aggregate of material, again, that's been compacted or cemented, then becomes a sedimentary rock. So next time you see a full-blown sedimentary rock, have a little compassion. It's been through a lot to become that sedimentary rock. So again, for the discussion of sedimentary rocks, we're going to explore this flow diagram. But again, we're not going to look at the weathering part of it. We're going to start with sediment and work our way down to a sedimentary rock. So the question at the top of your screen says, why is the Earth's surface 75% sedimentary rocks? Well, think about that. Where does weathering take place? Weathering takes place at the surface of the earth, not the interior parts of the earth. So you can kind of envision the lithosphere. And if you recall, we indicated that the lithosphere where we live basically is very, very, very thin. In fact, we used the analogy, I believe, in the intro part of the Earth chapter, where we said that if you take an egg and you reduce the size of the Earth down to the size of an egg, the lithosphere is about the thickness of the eggshell. So it's very thin. So on this little thin layer of the lithosphere, you basically have a dusting, if you will, of sedimentary rocks. But yet we live on the surface, and around us, about 75% of the rocks found in the lithosphere are sedimentary rocks, due directly to weathering processes. Okay, so what we're going to do then is we're going to take the sediments and we're going to separate the sediments into three broad categories. And this is where it gets a little complicated for students, because what students want to do is they want to memorize each one of these separated categories. What I would suggest that you do is, instead of memorizing each one of the categories, instead come up with a one-sentence difference that, in your own words, that describes the difference between each one of the categories. So let's go through and talk about the types of sediments in those three categories, and then from there, we're going to look at how they are lithified, and then we're going to classify them. So three categories of sediment. We'll start with the one up at the upper part of your diagram. There's a couple terms used, either clastic or detrital. And so the modern term, I believe, today is detrital. And when we say detrital sediments, we're talking about types of sediments that are composed of inorganic grains or mineral fragments, and it range in size from the size of flour, which is very microscopic, to the size of boulders. Okay, so clay particles, which is the size of flowers, to boulders. And these are inorganic grains. And what does that mean? That means these grains are basically the result of other rocks being physically broken down into smaller pieces, and they are not living. So detrital sediments are inorganic grains that eventually will be lithified together. The next category would be chemical sediment. And chemical sediment now forms by what we call precipitation processes. So these represent minerals that are precipitated from bodies of water, like lakes, rivers, or seawater in type environments. And when we say precipitated, that is a term that describes basically a solid being born out of a liquid. Okay, so precipitation in this case is a solid born out of a liquid. So we can have a huge lake, for example, and various processes will allow solids to come out of that lake, and we would call that chemical sediments. So to kind of review, detrital sediments are inorganic grains. Chemical sediments are precipitated type minerals. Then the last category at the bottom of your screen represents what we call biogenic. Sometimes they use the word bioclastic, and I think the modern word is organic sediment. So biogenic, bioclastic, and organic are all the same terms. And basically, this is sediment that are composed of animal and plant remains, hence the word organic. And so this is where we look at an organic type rock, and you're going to find fossils. Maybe you'll find shark teeth, skeletal fragments, plant material. Anything in which the rock is composed of that deals with organic would fall into the organic sediment category. So just to review, the three types of sediment categories, which we're later going to use for classification, we're going to look at detrital, which are inorganic grains, chemical sediment, which are precipitated grains or minerals, and then organic sediment, which is sediment composed of once living material, or maybe even living at the time. All right, so your job, I would suggest, is to, again, not memorize the three separated groups, but come up in your own words with a one-sentence description. So let's now take this sediment, either group, it can be either of the three categories, and let's go ahead and move down our flow chart that we showed earlier, and let's look at the lithification of sediment. We'll look at a couple ways common ways in which sediment can be lithified or formed into a sedimentary rock. And probably the first common way is the process of compaction. And very simply, when you compact something, you squeeze it together. And in order to do this from nature's point of view is you can take the overlying weight of sediment. So the more sediment you deposit on top of each other, layer by layer by layer, the bottom layers, excuse me, the bottom layer becomes more squeezed, more compacted, and the sediment grains get closer and closer together. It compresses the pore spaces, which pushes the particles together. If you look at by example under the compaction, you see a diagram that shows A, and you see that the particles are spaced far apart. We would say that the porosity, and we'll get to that a little later when we talk about water, but we'd say that the space in between the particles are a lot larger. Then under the compaction processes being squeezed, we take that unconsolidated sediment in A, we compact it, compress it, and you can see in B that now the pore space is being reduced. And now by that process of compaction, we're producing a sedimentary rock. Another very common way that sediment is lithified is through the process of cementation. And in this case, we've got water that's inside the pores or in between each one of the grains is squeezed out or expelled. And then the water carries different types of dissolved ions. Recall what an ion is. And the typical ions that are carried is iron, another type of ion called calcium carbonate, and silica. And when conditions are correct, the iron, calcium carbonate, or silica will precipitate out of the solution that it's being dissolved in or carried by the water. And then it acts as a glue or a cement, and it actually glues the particles or cements the particles together. And again, I call this a geological glue. So this diagram at the bottom of your screen shows a sedimentary rock, and you can see where this is a little cement and a little arrow pointing in there. And this rock has either been glued or cemented together. And again, the common cements are iron, calcium, and silica. So the question is, how can you tell, for example, if you have a sedimentary rock and you're a geologist and you're looking at the sedimentary rock and you need to decide, is it been glued by iron, calcium carbonate, or silica? So one of the ways is what happens to iron when it gets water on it. It rusts, it turns red. And so a geologist can look at the individual grains, and if you see rusty type iron oxide cement between the grains, then we'd say that the source for gluing that rock together was through iron precipitation. And how would you tell if a rock is glued together with calcium carbonate? Well, if you've been doing the lab, so this is for the lab folks, you find that calcium carbonate will always react with hydrochloric acid. So in a lot of cases, especially if you work in the oil business, if you're looking at a rock and you want to know if it's been glued together with calcium carbonate, which is very important in the oil industry, you can put a little bit of acid on there and you can actually see fizzing, or sometimes we refer to it as effervescing, but fizzing that goes on in between the pores. And that indicates to the geologist that this is a calcium carbonate cement. Silica cement, how would you know if it was silica cemented? Well, we learned from the minerals that silica is covalently bonded. It's a very hard substance. And so silica cement would be very, very hard to break. And in the oil industry, they don't like rocks that are silica cemented. They much rather take rocks that are calcium carbonate cemented. That's more conducive to oil. Okay, so now we're going to take the detrital sediment, and we're going to look at a picture of detrital sediment. We're going to lithify it, and then we're going to come up with a rock name. So in this case, in this level of the class, we're dominantly going to look at the textural characteristics of sedimentary rocks as opposed to the compositional characteristics. When we get to the chemical sediment, we'll rely a little bit more on the composition. But here in detrital rocks, we're going to rely on the textural characteristics. So let's take then gravel size sediment. So you look at the left part of your screen, you see gravel sediment, and typically ranging from pea size, so very visible, to larger. We lithify it, either compact it or cement it together, and this produces the sedimentary rock we call conglomerate. So conglomerates are typically lithified pebbles ranging from pea size to larger. You can actually apply a number to the size of the grains, and if the grains are 2 millimeters or greater, then it falls into the conglomerate type classification. And recall now we're looking at detrital sediment, so these are all inorganic grains. We can look at sand size particles, and remember, or at least know, that when we say sand, we're talking about a size range. And typically in a sand ranges from 1/16 of a millimeter to 2 millimeter. And a good example of sand size material is beach sand. So if we revisit the beach and you pick up that big handful of sand, that would be sand size. And sand can come into where it's very fine or it's very coarse. And this would be analogous if you went to the Home Depot and purchased fine-grained sandpaper, medium or coarse-grained sandpaper. All of that sand falls within the sand size particles. And so once that sand now becomes lithified, either cemented or compacted, it now becomes a sandstone. So a sandstone then represents a detrital type sedimentary rock. So on your screen, you see the E hanging down there. The E should be right up there after sandstone. So now let's drop down to particle sizes that are below 1/16 of a millimeter. And these now become finer particles. And typically we could say that these particles are the size of table salt. So it's less or smaller than sand size particles. And we lithify these type particles, and this now becomes a silt stone. So siltstones are a lot finer, if you will, than sandstones. Now, this is a legitimate test that sedimentologists do to distinguish the difference between a siltstone versus a sandstone. Now, in a siltstone, it's very hard to see the grains with an unaided eye. And so one of the techniques that a geologist uses to actually test to see if they're in a silt size range of grains is you actually can take the siltstone and rub it across your teeth. Believe it or not, that is a bona fide test that sedimentologists do out in the field. So they take this siltstone, rub it across the teeth, and if you can feel the grittiness across your teeth, then you are more than likely in the silt size. Now, you certainly would not want to do this test with a conglomerate. Think about that. So let's drop now to the smallest, finest sedimentary size particle. And this particle size is less than 1/256 of a millimeter. And basically, this represents the size of flour. And if you look at the left-hand side of your screen, the bottom portion, you see a micro electron scanning microscope picture of flour, or I'm sorry, not flour, but in this case, sediment. And you can actually see pore spaces. So it's legitimately a detrital sediment, but it's very, very fine. And when lithified, this becomes a shale. So a shale is a very fine grain sedimentary rock, almost analogous to clay. So clay would also represent that very fine grain detrital sediment. Now, a couple things to take home with this slide. One is, if you were asked how are detrital sediments, or I should say, how are detrital rocks classified with regards to texture? And we would say it's basically is classified based on particle sizes. So if you look at the conglomerate, the sandstone, the siltstone, and the shale, you find that from the conglomerate to the shell, it's decreasing particle sizes. And so from a textural standpoint, that's how sedimentologists identify the detrital part of sedimentary rocks. So for this class, you should be very familiar with what a conglomerate, sandstone, siltstone, and shale represent, and certainly be able to classify them based on the sizes of the grains. Let's now look at chemical sediments and the sedimentary rocks for chemical sediments. And so chemical sediment, as we said earlier, is typically formed by precipitation of minerals that are precipitated from either a lake, river, or seawater, probably more commonly from a lake or quiet waters in the ocean. Typically, surface water and groundwater will contain dissolved ions or chemicals in this case, creating that venue or creating the materials necessary for precipitation to take place to produce the chemical sediment. So precipitation of chemical rocks will take place in two common ways. The first way is through plants and animals. And so if you kind of think about oceans and lakes and areas that are swampy and quiet type environments, you have a lot of critters and animals and plants that live inside those waters. Well, as they grow and as they produce waste products and so forth, they have a tendency to alter the chemical balance of the particular water body that these animals are existing in. And so that alteration or that chemical alteration of the water can lend itself to various types of chemical sediments that would precipitate or come out of the particular water body. The other way that chemical sediments can turn into sedimentary rocks is through evaporation of chemically saturated waters. And so we'll do an example here in a second, meaning that if you have a body of water that's got various ions that are dissolved in this body of water, as this water body is evaporated, the concentration of ions get higher and higher. And once it reaches a certain concentration, the chemical reaction will take place, producing a precipitated solid. So two ways, plants and animals can change the chemical balance, producing chemical sedimentary rocks, or through evaporation processes of saturated water. So we're going to use the example of evaporation. So we're going to use the second way in how chemical sedimentary rocks are created. So in my example, if you look at my screen, I have a cross-sectional view of a little water body, quiet water body. It has sodium and chlorine ions that are already dissolved in the water. And what we're going to do is we're going to allow evaporation to take place in this water body. And so as evaporation takes place, what's going to happen to the water level? It gets less and less and less, which is now going to bring the sodium and chlorine ions closer together. In other words, it's going to concentrate the water body into sodium and chlorine. So the bottom picture on your slide shows the evaporational process. As you can see, the lake water has now gone lower. And so the lake body is now being concentrated in sodium chloride. And so now we're producing a chemical evaporite or chemical type sedimentary rock, which is known as halite, which is also a mineral. In this case, the sodium combined with the chlorine, and then it forms the table salt. And so this is a typical common process that takes place, takes place forming, in this case, sodium chloride. Now, this can happen with other chemicals. It doesn't have to be sodium and chlorine. It could be calcium and sulfate, which would form another type of chemical sedimentary rock that we call gypsum, which is also a mineral. So this picture here represents a chemical sediment deposition, and this is the Great Salt Lake in Utah. And for those folks who don't know where Salt Lake, Utah is, in your bottom left-hand side of the slide, it shows you the state of Utah, and then you can see where the circle is. It shows you the Salt Lake. And Salt Lake basically is a type of lake in which there's more input of sediment than what goes out. And of course, there's a lot of evaporation that takes place. So envision this lake analogous to the previous slide, where lots and lots of evaporation is taking place, and of course, leaving behind concentrations of sodium and chloride, or in this case, layers of salt. I recall when I was several years ago, my family and we took a trip up to Idaho to see my parents. And I thought this time I'd like to travel through Salt Lake because I've never been through Utah. So as we progressed and drove up to Idaho, we went through the Salt Lake area. And right before Salt Lake City, we stopped the van. I got out and I walked along the Salt Lake, and it's very interesting when you walk along the Salt Lake because it's a thick sequence of salt layers, and as you walk, it's kind of a deadening sound. It's kind of eerie, to kind of walk along those salt flats. But something interesting is I went back to the van, and before I left Bakersfield, our home, I went and got a box of snails. And I thought maybe, as I walked out, I took the box of snails out of the van and I walked to the Salt Lake and I opened the box, released the snails because I thought they'd like, to be released. And as I released them, I said, okay, have a good time. So think about that. So this picture in the lower left-hand part, lower right-hand part of your slide shows the actual lake. And because it's so concentrated in sodium, chloride, or salts, the density of the water increases, and one can actually just sit there and float in the lake without even any struggling because of the density. Now, this picture you're seeing, I have no idea who this person is. This is gleaned off of the internet, no affiliation with me. So, looking at chemical sedimentary rocks, here we can look at both texture and composition. And so remember that in the chemical sedimentary rocks, they've been precipitated or from a source or the result of evaporation. So a couple things going on here. One is I want you to look at the pictures of the gypsum, the halite, and the limestone. And I want you to recall and look at what you observed in terms of the conglomerate, sandstone, siltstone, and shale. So for example, how would you tell texturally the difference between a chemical sedimentary rock versus a detrital sedimentary rock that we just looked at? Just by looking at these pictures, what would you conclude is a huge textural difference? So most students in class will stare at this for a minute, and at some point somebody actually comes up with the correct response. And that is, if you look at the chemical sedimentary rocks, you do not see grains. There is an absence of visible grains. Compare that to the detrital rocks. Detrital rocks, you're going to see grains. And so when someone brings me a sedimentary rock, that's one of the first things I look at is the absence of grains or not. So now we can take the chemical sedimentary rock one step further. So texturally, it lacks grains, but chemically, how can you tell if the chemical sedimentary rock is composed of calcium carbon or calcium sulfate, sodium chloride, or in this case, limestone, calcium carbonate? Recall the acid test. So during the acid test, if you put hydrochloric acid onto the calcium carbonate rock, it will definitely fizz and effervesce. And that tells the geologist that this is an environment in which this rock was produced with calcium carbonate. The halite, if you put acid on it, will not fizz, but you certainly can taste the halite and you would certainly taste the salt. I would recommend that you taste it first before you put the acid on it. Gypsum, the calcium sulfate, that would be readily identified based on its hardness. So gypsum is about a hardness of number 2, And so that would be easily scratched with your fingernail. So these three common chemical rocks are very easy to identify if you implement the acid and you implement the hardness test and even the possible taste test. But the fact is that the chemical sedimentary rocks lack grains, visible inorganic grains, and the detrital rocks certainly have grains. Our last category we're going to look at is organic sediments and organic type sedimentary rocks. And so again, these are types of rocks in which the sediment has been lithified, and there's evidence of shell fragments, bones, teeth, says plant fragments, wood roots, anything that's organic would give rise to the biogenic or organic rock. And probably the most abundant organic sedimentary rock on Earth is referred to as a limestone. And you're probably thinking, well, wait a minute, did you not just show me a limestone in the chemical sedimentary rocks? And the answer is yes. But in this case, the limestone is going to have some type of organic type of concentration, organic material associated with it, therefore putting it into the organic rock. So you can have a chemical limestone, or you can have an organic limestone. And most organic limestones are composed of calcium carbonate. Sometimes they use the term dolostone or aragonite. These are all common organic type rocks, lithified shells, skeletal material, and so forth. So organic or biogenic, bioclastic rocks then again result from animal plant material. The term clastic is a term that indicates that these rocks contain some type of particles, in this case, fossils or parts of plants, shells, and so forth. So some of the common organic rocks that I put on the screen would be fossil limestone. So here's a limestone that would fizz with acid, but also contains fossil parts. Here is cemented shell fragments. So you look at this type of rock, and it's composed of all shell fragments that have been cemented together. This is referred to as coquina. And then I put on the lower right-hand part of your screen microscopic fossils in terms of chalk. So chalk really is an organic sedimentary rock because of the microscopic fossils that exist. So this last slide for part 2, in terms of looking at sedimentary rocks, is a sedimentary rock classification summary tree. And so, I've basically in the last 8-9 slides, I've given you a lot of information about sedimentary rocks. And literally, folks can spend an entire career taking geology courses and becoming a sedimentologist and just be looking at what we did in 9 slides. I mean, you literally could get a PhD. So what I gave you a lot of information. So what I tried to do here is give you these sedimentary rocks and divided them up in their 3 classification categories. So this is a really good summary slide that I would encourage students to look through instead of memorizing. Try and learn the concept and put the concept in your own words. So the first category we looked at were detrital sediments. And if you follow the arrows, composed of inorganic grains, classifications based on grain sizes, inorganic grain sizes, and based on decreasing grain size. And there you see conglomerate, sandstone, siltstone, and shale. Then we have our chemical sediments, again, following the arrows downward, formed by precipitation, either from plants and animals or evaporational processes. Classification is based on lack of grains and its chemical composition. I've given you 3 common chemical sedimentary rocks: gypsum, halite, and limestone. And then we look at organic chemical sediments, typically composed of animal parts. Classification is based on observed fossils, animal parts, plant secretions. And then the 3 common organic rocks I gave you were fossiliferous limestone, sometimes called fossil limestone, coquina, and chalk. So it's your job then to be able to, again, describe each one of the sedimentary rock groups, but instead of memorizing, try and find differences. Try in your own words and paraphrase the difference between detrital, chemical, and organic type rocks. And then you'll certainly want to be able, for test purposes, to associate the particular sedimentary rock type with the type of sedimentary rock category.